So thank you very much for the introduction. Thank you very much for the invitation. It's a bit of a pity that I can't actually be there in person because travels are still complicated and very restricted. And I would definitely love to be in Korea right now. But I think I'll manage to do this remotely. So when I was invited, I was asked to talk a bit about technical decisions and technical design decisions involved in building post-quantum crypto schemes. And we'll talk about this a little bit. But then when preparing the talk, I actually realized that something that's maybe more interesting to talk about is my personal experience in these 4 years now of NIST post-quantum crypto competition, actually a bit more if you count the preparation time in. And one thing that I should mention from the beginning is that this talk is very highly biased. I mean, if the word personal experience didn't make it clear in the title, it's biased in all kind of ways. It's just a matter of fact that I have something to gain or to lose depending on the outcome of the NIST post-quantum competition. So anything that I say about this topic is not, I think, inherently objective. It can't be. Also, I'm an academic. I work at Max Planck. I work at a university. I've never worked in industry. And that gives me sometimes the luxury to ignore certain real world issues. There are certain aspects that I think companies need to worry about. They need to worry about their shareholders. They need to worry about legacy code and technical debt that they have. And I have the luxury to not care about this. And actually, I think about what are technically good solutions, at least solutions that I think are technically good. And I still aim for a real world impact with my work. So I think I'm always interested in solving real world problems and contributing to actually, crypto that will be deployed. Large parts of my talk in this reflection on these 4 years are looking back and thinking about what could have been done better. And to some extent, this refers to what could have been done better by submitting teams, including our submitting teams. And a lot of that also refers to what could have been done better by NIST. So I understand many of the decisions that NIST made, but I'm just thinking that, well, if you want to run such a project again, NIST or anybody else who wants to standardize cryptography through an open process, then maybe these are good things to think about and maybe improve the process. So it's meant as constructive criticism. And I'll try to avoid finger pointing in this talk. I don't like this very much. I will give a few examples of things that went badly wrong. But when I give examples that actually say where we found these examples, I'll try to restrict myself to examples in schemes and submissions that I was involved in. So that at least I'm finger pointing only at myself. All right, so why I think I was invited to give this talk, the introductory words already said this a little bit. So I was involved in 7 submissions to the NIST PQC project. And I should say, I will come back to that in the next slides, with very different amount of contribution to the different submissions. And all 7 advanced to round 2. Actually 5 advanced to round 3. So 4 are finalists and 1 is listed as an alternate scheme. And I'm also at the moment working, I'm working on post-quantum crypto and on engineering aspects and applied aspects of post-quantum crypto. And I'm doing this within an ERC starting grant project, which is called EPOC, Engineering Post-Quantum Cryptography. And there's sort of 2 directions that we're looking into there. This is efficient and secure implementations, and how we use the post-quantum primitives that maybe eventually get standardized, probably eventually get standardized, to build protocols, and how do we do this efficiently. Now, these 7 submissions that are originally submitted to the NIST PQC project, let me briefly mention a few words about them. The first one to mention is probably New Hope. New Hope goes back to a joint paper with Adam Alkim, Leo Dukas, and Thomas Pöppelmann that we had at Usenix 2016. It was quite successful. It won the Internet Defense Prize. And the scheme that we proposed there, the New Hope scheme, was used in the first post-quantum TLS experiment by Google. So NIST actually wrote us an email and said, hey, we would be happy if you submit this to the NIST post-quantum competition. So we did. And then we got kicked out with this submission after round 2, which I actually think was a really good decision. Because I'm also involved in another lattice-based key encapsulation mechanism called Kyber. And at least to me, I would see it as a successor to New Hope. It learned a lot of lessons from New Hope. It takes a lot of the design decisions from New Hope, but it improves on it. So I would, to me, it makes a lot of sense that New Hope got kicked out and that Kyber advanced to the list of finalists. Then I'm involved in another lattice-based plan, that's NTRU, and that goes back to a paper that John Skank and Andreas Hulsing and Joost Reinefeld and me had at CHESS 2017, where we tried to build a key encapsulation mechanism from NTRU and make it very efficient. And then later that got merged with another NTRU submission. So now we have a rather big submitter team and have more parameter choices. And really, John took the lead in all of this. So he turned our CHESS paper into an actual list submission and really is the primary submitter of this, at least of the original submission. And then while the NTRU team, of course, so this other submission also contributed afterwards. And then I'm involved in Classic Macalese, and that's a really big team. I'm involved because in 2013, I had a paper together with Dan Bernstein and Tung Cho on implementing Macalese efficiently using bit-sliced arithmetic. And some of that code ended up there, and I said, well, I'm happy to endorse that scheme. Again, many other people have contributed much, much more to this submission than I have. I'm happy to endorse it occasionally and contributing to discussions, but I'm certainly not the one driving this submission. On the signature side, there is MQDSS. That's one of the schemes that got removed after round 2. And again, I very much agree with that decision by NIST. It goes back to an Asia Crypt 2016 paper to try to build signatures from the MQ problem in a way that there is a reduction from MQ to the security of that, or the hardness of breaking that signature scheme. And I think it's a very interesting proposal. Quite interestingly, something that I learned through this proposal is the proof that we proposed is non-tight. And then Greg Zabarucha and others presented an attack against this, which is not invalidating any of the statements that we're making, but the attack is basically hiding in the non-tightness of the proof. And it got removed partially because of this. Probably there were some other reasons. I think there is just, for practical use, there's better schemes out there. Then I'm involved in dilithium, which together with Kyber forms the crystals suite of lattice-based post-quantum cryptography. So dilithium is the signature scheme, Kyber is the key encapsulation mechanism. And then again, with a rather big team, I'm involved in Sphinx Plus. That's a stateless hash-based signature scheme going back to a Eurocrypt 2015 paper on a design called Sphinx, which we improved for the NIST competition. And really also here, I mean, I contributed quite a bit, but really Andreas Hulsing is the person driving this project forward, this submission. Now, when I was asked to give the talk, as I said, I was asked, so can you give us something on design decisions for building good schemes, or at least, well, schemes that are above average successful in the NIST competition? And I thought about this, and well, there's lattice-based schemes in here, there's code-based scheme, there is a multivariate scheme, there's a hash-based signature scheme. So what do they have in common? Like, is there some underlying design decisions or some underlying design approach that they have in common? And I'm not the person doing the security proofs. I'm not the person doing the cryptanalysis of the underlying mathematical problems. So what would it be that maybe I contributed to this design that maybe made it successful? I can only a little bit guess here. And I wouldn't say that it's like an individual small decision that all of them have in common. It's maybe more of an approach thing. So the traditional approach of building cryptography, and in particular asymmetric cryptography, is that there is, well, cryptography happening, which is a lot of mathematics and algorithms. And you come up with a scheme that, well, lives in the realm of mathematics. So expressed in terms of operations in mathematical structures. And then that is given to people who do implementation, so engineers. And they write software for it, and they write hardware for it. And in the end, build a cryptographic system, so something that you can actually run to protect information. And I think what we did in all of those designs is, well, a more holistic approach. So we brought in aspects of implementations much, much earlier into the design process. So issues that pop up when you're implementing things, and try to implement it efficiently and securely in software and hardware. And then the result is not just a scheme, but it's actually the scheme together with a prototype system. And that's sometimes an iterative process where you're designing something and then you try to implement it, but then you update the design based on some experience that you make during the implementation. I believe that with this more holistic approach, we obtain schemes that have better performance, that have better implementation security, or at least are easier to implement securely. And with a bit of a stretch that I'll come back to at the very end of my talk, these schemes are hopefully more likely to be correct or can more efficiently be proven to be correct implementations of those schemes. Now, that was my high-level thought of like what actually made these schemes maybe successful in the NIST PQC competition. And then I thought, okay, can I give some examples of where this holistic approach actually changed the design? And I can give you a few examples. There's probably many more, and sometimes it's not even possible to just pinpoint it completely to one thing. But here's a few things that I think are really engineering motivated in the design. The first one is dilithium versus dilithium G. So if you look at our paper of dilithium, which was at CHES 2017, I think, well, we described dilithium, which uses uniform sampling of noise. And in the appendix, we describe a variant, which is called dilithium G, that uses discrete Gaussian noise. And in the realm of mathematics, it makes perfect sense to use discrete Gaussian noise because your signatures become smaller. And we want small signatures. This is actually a pretty critical performance criteria. However, discrete Gaussian sampling is very hard to implement securely. It's easy to leak secret information through timing when implementing it naively, you will. And making it secure makes it rather slow. Also, I mean, generally randomness is hard to test for, but discrete Gaussian with a very high standard deviation is extremely hard to test for, much harder even than uniform noise. Another example is how we're sampling the matrix in Kyber. So in Kyber, and I'm using a concrete parameter set here as an example, it's Kyber 768. We need to sample 9 polynomials. Each polynomial has 256 coefficients. And each coefficient needs to be sampled uniformly mod Q, where Q is a prime. Now, the way to do this is we're taking a seed, it's a public seed, we're expanding that seed through shake, and we look at the output of shake and run rejection sampling on it. So basically, we take a few bits at a time of shake output, and we see if this is bigger than Q, then we throw it away. If it's smaller than Q, we accept it as a coefficient of one of the polynomials. Now, in a simple cost model, the most efficient way to do this is that you're taking one shake output, and you're running rejection sampling on this one output, long output of shake, to obtain all the polynomials. So then you need 9 times 256 coefficients sampled from one shake output. That's not what we're doing. What we're doing is we run 9 independent invocations of shake, one for each of the polynomials, and then run rejection sampling of those. Now, shake generates output in terms of blocks. And while at the end, we just have some output of shake left over. And actually, when we're using 9 independent invocations, we have more left over. We generated more output than we actually need to generate. We're throwing away more computation. So why are we doing this? Well, if we're doing this, we can vectorize this. So if we have a computer with SIMD instructions, we can compute these independent parallel shake invocations much, much faster. And shake is notoriously hard to vectorize internally, but now with independent invocations of shake, we can do this extremely efficiently. You might still think this is a disadvantage if we are doing this on small embedded microcontrollers that do not have vector instructions. But even there we gain something, because we can very efficiently and easily implement the sampling of the matrix together with the matrix vector multiplication afterwards with a small memory footprint, which is a very critical criterion on embedded microcontrollers. Yet another example of where really engineering thoughts influence the design process is that in lattice-based key encapsulation mechanisms, when sampling the secret and sampling the noise, you can obtain a much lower failure probability, which you want, when using fixed weight sampling. So fixed weight means that you have a fixed number of non-zero coefficients. We're still not doing this. This, by the way, also has implications on the security analysis and all of this, so it's not a purely engineering driven decision. But we don't do this in New Hope, we didn't do this in Kyber, and we didn't do this in Intro HRSS, so our original entry submission. Why not? Well, if we want to obtain something that has a fixed weight, we need to compute, or at least the typical way to do it, a secret permutation. One way to do this is through sorting. So basically, you're sorting an array according to random integers. The problem with sorting is you can do this efficiently without leaking through timing. At least on many architectures you can. Maybe on all architectures. But the simple way to implement this is to just, use a standard library and call sort. And that is not going to be constant time, and it's going to leak secret information through timing. So make it simple, make it easy to implement the scheme securely. And then finally, the one that I like very much because it didn't influence the design, but it influenced the proof. In Sphinx Plus, when we implemented this for the software implementation, we used an abstraction layer to modularize the code, which we called tweakable hash functions. And that was very natural to do in the software implementation. And then at some point, when discussing with Andreas, we came up with the idea that can we use this to also modularize the proof? Can we assign a security notion to this, abstraction layer of a tweakable hash function? And then build the proof in two steps. One being that we show that certain constructions of tweakable hash functions achieve this security notion. And then on top of that, build the whole rest of the proof. And it turns out we could. And that went into our CCS paper describing Sphinx Plus signature framework and also this proof technique. Now, for the rest of the talk, I will talk a bit more about my experience through this NIST competition. And I'll organize this in two parts. The first part is on software implementations. It's just my area. This is certainly where I've gathered most of the experience. The second part, just already as a spoiler, is going to be random thoughts. So it's lots of small things that I've noticed here and there that I think are worth reconsidering, at least when running a similar competition again. Now for software implementations, when you look back to 2017, when we were supposed to submit our proposals, there was, of course, a requirement by NIST for what we had to submit for software implementations. And just quoting from the call for proposals, we were supposed to submit a reference implementation, which was supposed to promote understanding of how the submitted algorithm may be implemented, and an optimized implementation targeting the Intel x64 processor, 64-bit implementation, which is intended to demonstrate the performance of the algorithm. Now, quite interestingly, both implementations shall consist of source code written in ANSI C. I'll come back to that in a moment. Then there were some permitted external dependencies. There was NTL, number theoretic library, GMP, the GNU multi-precision library, OpenSSL, primarily, I think, for underlying symmetric crypto, and then the extended KpqC code package, XKCP. For the API, NIST decided after some discussion to follow what the SuperCop benchmarking framework does. And that has some implications, and some of them were discussed a bit before, and some of them I think are worth mentioning. One of them is that signing does not produce a signature. It produces a signed message. And verification does not get a message and a signature, but it gets a signed message and, returns true or false and returns the message when you're verifying. This has some implications. For example, if you want to take a message and put two signatures on them with two different schemes, that's not actually all that easy. You need to create a signature scheme that combines these two signatures. Okay. It's an interesting design decision. It has its advantages and disadvantages. Randomness is sampled internally. So when you're running key generation, you're not providing the randomness as an argument, but you're basically sampling through the call to random bytes function randomness internally. Similar for, let's say, encapsulation in a CAM. And there's no batching. So all of the API is performing one operation. So one generates one key pair or encapsulates one key or signs one message and not a whole bunch of messages. So that's also something I will come back to at the very end of the talk. Now, following these requirements, teams wrote software, submitted software, and about a year later, Dan Bernstein summarized the situation of these software implementations with the following quote. He said, NIST PQC, despite being an important and timely project, has produced the largest regression ever in the quality of cryptographic software. This will not be easy to fix. Okay, now Dan likes to make bold statements, and this is certainly not an exception, but there's certainly some evidence when looking at the submitted software implementations to support that statement. I collected just a few examples here to show you what kind of things you find in the software found, at least at the time, that was submitted to NIST. And I'll start with the really nasty examples. So there was one submission where we found a function that returned the pointer to a local stack variable. Now, the calling function receiving that return value can basically do only one thing with it. That's dereference. That's what you do with a pointer. But at the point when you dereference, that memory location isn't a valid memory location anymore because the stack frame that it belonged to has been popped from the stack. So this is, in basically any scenario, undefined behavior. It's absolutely terrible. So when I looked at this, I was like, how can this possibly work? Well, the simple explanation is that this function was never used in the code. I have no idea why it was there. But there were also examples of terrible code that was actually used. So another very puzzling example is that there was one submission that claimed in the specification document a certain size of keys, and I think also ciphertexts, stuff like that, of cryptographic objects. And the implementation generated stuff that was way bigger. And the reason was simply that actually compressing the elements to the number of required bits that in the mathematical description was there was never implemented. So the implementation didn't match the spec at all. Another favorite of mine was there was one Fujisaki Okamoto transform. So Fujisaki Okamoto transform makes sure that at decapsulation you're re-encrypting and you see if the ciphertexts match. Now, for this re-encryption during decapsulation, you need the public key. But the public key is not being passed as an explicit argument to the decapsulation. It's just not part of the API. So what do? Well, usually what you do is you just store a copy of the public key as part of the secret key, because the secret key is passed to decapsulation. And then you have access to the public key. But there was one submission where this didn't happen. The public key was never written down as part of the secret key. The decapsulation simply assumed that it would be in memory behind the secret key, just read the secret key out of bounds. And it happened so that in all of the test cases, the public key was actually coincidentally stored behind the secret key. And so the test cases passed, although this was undefined behavior in all kinds of ways. We found more out-of-bound reads where a scheme only worked because by coincidence, somewhere in memory, there were zeros stored. Admittedly, it's not the most unlikely value to be stored in memory, but still you can't assume anything. And it's also undefined behavior. We found out-of-bound writes where really I think you can just hope for the best because you might be overwriting all kind of critical information. So this is, I think, nasty examples because those are being caught by various standard testing tools and static analyzers. There's also a few more interesting examples. So there were two schemes, so the early implementation of the lithium and then also an early, well, somewhat later implementation of Falcon, both lattice-based signature schemes that had a bug in the noise sampling. And, well, everything worked, but it was not secure. And that is at least something where you need to have an understanding of the specification. This is not something that simple black box testing or static analysis would catch. Another interesting one, and I'm totally guilty for this one, is that the decapsulation in Kyber uses implicit rejection. So when the Fujisaki Okamoto transform basically produces a failure, so notices that the ciphertext produced in re-encryption doesn't match the received ciphertext, then we just compute a pseudo-random key that depends on the ciphertext and a long-term secret. And that's totally fine, and the implementation did all of that. It additionally returned -1, because many practitioners say, well, as early as we know that something has failed, we would like to know, because then we can abort further computations. The problem is that this is incompatible with assumptions in the proof, in the security proof, which really needs that we're not leaking if things fail or not. So, well, that was removed. Maybe last thing is that many implementations had timing leaks, and some of them, maybe you could say it's not a real bug because they never claimed that they wouldn't have timing leaks, and then you can argue how important it is to not have timing leaks. Other implementations made claims that they don't leak through timing, that they're constant time, and still leaked. So then I think it's pretty clearly a bug. Now, what are the underlying reasons for this rather terrible software quality? I can only speculate a little bit here, but I think there's some truth in what I wrote down on this slide. So I think there is a different understanding of what cryptographic software means. And people who are working commonly or frequently on cryptographic software that gets actually used in the real world, who are contributing to cryptographic libraries, maybe are maintainers of a cryptographic library, like Dan Bernstein, for example, who came up with this bold quote. They think about cryptographic software when they publish it as it should be production quality. It should be ready for real world deployment, or at least, well, it might need some more testing and auditing, but at least that's the goal of it, that we're getting there. And I think for some submission teams, at least, it's a proof of concept where academics were showing that the scheme can be implemented, maybe how it can be implemented. We show that it actually works, but that's it. And then we leave it to engineers. So in this traditional second stage of the implementation, to come up with something that is actually secure and good. There's some more reasons. So the C programming language makes it fairly easy to get things wrong. There's various mechanisms we know to avoid certain classes of bugs, but C is not exactly known to be to make it easy to get things right. Then ANSI C, as required in the submission, in particular without intrinsics, is not super useful to illustrate performance. So I think one of the most important techniques to optimize performance is vectorization. And that's something that compilers are unfortunately still not very good at doing automatically. So the best way to actually optimize software is to write parts of it in assembly, or at least in a block of intrinsics. I think there were multiple teams who didn't have anyone on board who has a lot of experience with implementing cryptographic software. And well, then schemes were designed and afterwards maybe given, I'm speculating here, to a grad student to implement that. And this is, you can say it's a disadvantage of those schemes who maybe came up with actually brilliant thoughts on the design, but then, well, this engineering input didn't come in. Also resulting in the end, probably not the best implementations. Another thing is that, well, they are all new schemes. We were supposed to propose new schemes. So there are no known test vectors yet. There's many tests or many bugs that can be caught by comparing to test vectors if you can trust the test vectors. And while obviously we didn't have test vectors, the reference implementations were the first ones to produce those. So if they have a bug, the test vectors are wrong, and other implementations may then also be wrong. Finally, I would say that it was a little bit unnecessarily hard to get software right. And let me in the following explain what I mean by this. it essentially boils down to an experience that I've made as a teacher. So as a teacher, I've observed that the more time you put into designing an exam, the less time you need grading it, at least if you carefully plan for this. So I think when running a standardization project like NIST PQC, it's worth investing some more time into software implementations before the competition starts. Some examples of what I mean is it would have been probably useful to have one example implementation. It can be pre-quantum scheme, it can be a simple scheme, just illustrating how certain things are being done in the API. It would have been very useful to provide a test harness. Of course, a black box test harness. We can't have unit tests. We don't know what schemes are being submitted. But the kind of testing that I'll show on the next few slides you can do on any scheme, and providing that test harness to all submission teams would have avoided a lot of bugs and a lot of, well, unnecessary weaknesses in software. Maybe a next step would be to have an interactive system where submitters can send software, it runs tests remotely, and then provides the feedback from running those tests. And then finally, we also need to talk about benchmarking platforms. And it might be an idea to provide access to a benchmarking platform so that people optimizing code at least know how things are going to be benchmarked and on what platform. It's sort of the same platform for everyone. It's of course always easy as an academic to say what should have been done. So a bit more of a year after the NIST competition started, we had that discussion, and we said, well, it would have been nice if that had been done. And then we said, okay, let's do it. Let's at least retroactively implement such a system and try to come up with clean software implementations that are better tested. And together with Matthias Kanwischer, Joost Reinefeld, John Skank, and Douglas Tibila and Tom Bichers, we built a system that we call KpqC, which is a GitHub repository. It has extensive continuous integration testing. The goal was to collect clean C implementations of all round 2 candidates. And then we updated the goal to focus on round 3 candidates when round 3 came out. We wanted this to be easy to be used in other projects, this code. And we wanted it to be a good and easy to use starting point for architecture-specific optimizations. We also thought that, okay, longer term, if there's interest, we could think about implementations with architecture-specific optimizations. There's some work in progress on that. We also thought about implementations in other languages, and that has never really happened. Then we needed a definition of what we actually mean by clean. So what kind of tests, what kind of requirements should we have on the software? First thing was that it's valid C99, the code, that it passes functional testing. We have some tests that API functions don't write outside of the buffers, don't require aligned pointers to be passed, that it passes without compilation without warnings with rather extensive warning flags with both GCC and Planck. It also passes similar things with the Microsoft compiler with a warning level 4 and WX, so extensive testing. It produces consistent test vectors across runs. This is all rather simple tests that you can run completely black box on any code. It produces consistent test vectors on big endian and little endian machines, which actually several implementations didn't do because the compression to byte arrays was not, depended on endianness. And it produces consistent test vectors on 32-bit and 64-bit machines. Some more stuff, we decided that we want to run Valgrind over it. So I wanted to run address sanitizer over it and the undefined behavior sanitizer. And there should be no errors or warnings reported by those systems. And we wanted to have very limited dependencies. So after looking at the schemes, most of them only need as external dependencies, well, some way to obtain random bytes, and then some symmetric crypto. So we implemented those, provide that to all schemes. Easy to replace by an external optimized implementation, and fairly easy to use inside this software. We wanted that all API functions return 0 on success and negative on failure, where I should say that something like the failure of re-encryption in the FO transform is not a failure in that sense. But a failure would be something like trying to read a public key that is not in the right format, for example. No dynamic memory allocations, so no malloc and free. We want this to build under Linux, Mac OS, and Windows without warnings. We want all code to be namespaced so that it can be easily integrated elsewhere. And we wanted to have license and meta information. So meta information being who the authors are, for example, in a somewhat standardized format. That, I think, was pretty much uncontroversial when we discussed this. And then there were a few controversial bits, namely that we actually, in the end, decided not to allow variable length arrays. That's a bit stupid, but the reason is that in order to build software under Windows, this is required, because the Windows compiler doesn't support this. We wanted separate subdirectory without any symbolic links for each parameter set of each scheme. Background being that then it's very easy to just grab the code and drop it into somewhere else, but that also means a lot of duplication of code. We didn't want code that has heavy if-defs everywhere. It should be easy to read code where you understand what is happening when you compile the code without having to dig through all of the hierarchy of whatever macros. So we wanted if-defs only for header encapsulation. No stratification macros for similar reasons. Some controversial discussion about how do we deal with very controversial warnings. So for example, the Microsoft compiler warns when you're using a unary minus on unsigned integers, which is very well defined and actually used by quite a bit of code as well as part of timing attack countermeasures. And you can write this differently, but it's actually not really, it doesn't make any sense to write it differently because it's really well defined. So I think in the end, we resorted to silencing the specific warning. And then we wanted argument names of functions to be consistent between header and C files. Makes code more readable, makes it more readable to extract what is happening just from header files, makes it a bit more tricky to use in C++. There's some limitations and there's some lessons that we learned through doing all of this. Well, we learned, I didn't know this at least, that the Microsoft compiler does not support C99. So that's why in the end we can't have variable length arrays. We learned we used public services for continuous integration testing. And well, at some point, these tests actually ran for a pretty long time. And that imposes pretty serious limitations. So they time out after some point, which is understandable, but it's at least also interesting to notice. We're not yet testing constant time behavior. We would like to verify that implementations don't leak through timing. We could do this using Valgrind with uninitialized secret data as a dynamic check, and that is actually what SuperCop is doing now. It adopted a technique known as timecop. Doing this, we could maybe also integrate that. It's sometimes a bit more, well, it's a bit tricky to even come up with the right definition of what constant time means, at least for some of the schemes. There's also the alternative of using something like CTVerif, which does static analysis, has stronger guarantees, but it's much, much harder to deploy. We also noticed, so some of the environments that we're testing in particular, big Endian environments, I think, are running in an emulator in QEMU. And there we can't run the Valgrind test. So Valgrind doesn't work together with QEMU. Okay, so this is something that, well, we learned, and I think at least some of that effort, something like that would be useful to have in place before a competition starts to ensure that submitted software has some minimum quality requirements, which makes it easier to optimize, it makes it easier to read the software, makes it easier to test the software, to benchmark the software, to improve the software. Talking about benchmarking, my understanding, and that may be wrong, is that the main benchmark provider for the NIST post-quantum competition is the EBEX benchmarking project with the SuperCop benchmarking framework. So for those of you who are not familiar with it, it's a huge benchmarking project by Dan Bernstein and Tanja Lange. Started, I think, probably more than 10 years ago, has collections of many, many cryptographic algorithms, different implementations of those algorithms. It's benchmarking them on a variety of architectures and microarchitectures, really gathering a whole lot of data. Much, much smaller and focused to just one architecture, microarchitecture actually, is a project that, together with Matthias Kannwischer and Petri Reinefeld and Stoffelen, we came up with that is benchmarking on an embedded microcontroller, the PQM4 project. So benchmarking on the Cortex-M4 only. And again, my understanding is that for benchmarks on the Cortex-M4, NIST is primarily looking at this. I would really hope that I'm wrong with this assumption. I would be happy to be told that this is just not the case, because the big problem with this approach is that these benchmarks are not independent. And I think to get widespread acceptance of the process that NIST is running, it is a problem that there is a massive overlap between the set of submitters and the set of benchmarkers. And I think benchmarkers is, strictly speaking, not an English word, so I put it in quotation marks, but I guess it's clear what I mean here. It might be just that there is an unfair advantage to the submitters who are running the benchmarking framework. And I'm not even saying that you're intentionally skewing benchmarks to make your schemes look better. That is, I don't think anyone is doing, but it's, the benchmarking framework much better. It's much easier to write software that that gets into that benchmarking framework, integrating it, running benchmarks whenever it's suitable when you needed them for a paper. I don't think this is entirely fair. Probably what would be more fair is, so duplicating something like SuperCop, I think, is not feasible for competition. It's also not required. So I think it's a good idea to fix a few microarchitectures, maybe just 3. Tell submitters that they should optimize for these microarchitectures. And microarchitecture, so what NIST wrote saying, the Intel x64 processor, there's many, many different Intel 64-bit Intel processors following the x64 architecture with very different performance characteristics. So fix really which processor exactly, ideally what compiler, what operating system, how much RAM, all of it. Say how the benchmarks are being run and publish this way ahead of time. Ideally also with discussion with the community if the benchmarking methodology makes sense or not. And then maybe, if required, give submitters access to the benchmarking platform. So I don't think it's fair to assume that everybody can just buy the hardware, set it up the way that it should be set up, and run it themselves. So I think giving access to it would be maybe a more fair approach for doing this. To wrap up the part on software implementations, let me talk a little bit about the C programming language and why we're still using it, or maybe why we shouldn't be using it. So I understand why we're using it for all these implementations. It's still what most cryptographic libraries are written in. It's easy to use as a starting point for more optimized implementations. But if you want a reference implementation that illustrates how something can be implemented and how it works, I think it might be better to ask for an implementation in Sage or in Python, maybe. It's going to be way easier to read. It's also going to be easier to write, in particular maybe for people who haven't been writing cryptographic code for the last 10 years. It is also less temptation then to use this for benchmarking. So you will find many academic papers reporting benchmarks of reference implementations, although the reference implementations were never actually meant to be performance optimized and were never really meant to be benchmarked, I guess. Downside of that approach is that if you have Sage code, it's somewhat less useful as a starting point for optimization. Some other idea, how about using Rust? If we want a low-level system programming language, then Rust has actually quite a few advantages over C. It's, I would say, a bit harder to write code in Rust, but it's much easier to write code safely to obtain memory-safe programs, for example. And I would also say it's easier to write correctly. There's many checks that Rust integrates. So if you have a program that actually afterwards compiled and runs, it's much more likely to be correct than a C program that compiles and runs. Finally, how about using HackSpec? This is a project mostly by people in INRIA in Paris to come up with a specification language for crypto primitives and more. And it's a subset of Rust, so the Rust compiler will just compile it. You can just simply run it. And it has some libraries implemented that make it fairly easy to implement cryptographic routines, so many of the say standard building blocks that you need are already available. And it has interfaces for computer verified proving of properties of the scheme and the software. At the moment, as far as I know, it translates to the F-star proving framework, but there's also plans to translate that to, for example, EasyCrypt. All right, that brings me to part 2, random thoughts. And in my abstract, I promised that I would talk a little bit about the social aspects of the NIST post-quantum competition. And when preparing the talk, I dearly regretted having said that. But as I promised it, I kind of need to do it, right? So let's get this out of the way. I decided to put one slide on my experience with the PQC forum mailing list. So I think the PQC forum mailing list has a lot of really valuable, constructive, open scientific discussion. Unfortunately, this is not what the PQC forum mailing list is primarily known for. And that is because you also find a lot of really big egos. You find personal attacks. You find what I would call sniping at maybe other candidates that are promising or perceived as promising competition. And quite often, these aspects blur the constructive and actually scientifically interesting aspects that are also going on there. I should say I'm also guilty here. So there's also one posting to that mailing list that I afterwards had to apologize to a few people, and I did apologize. I think it was not appropriate. But I think it's, as a community, I think there's a way to do better than what is happening on that mailing list. What we also see, I think that's the case in any social environment, is that there's a few people who are very loud, and of course, literally loud on a mailing list, but there's some people who write a lot and use very strong wording, so they are sort of the written equivalent of being loud. And well, as always, that doesn't necessarily correlate with being right. The tricky thing is it also doesn't correlate with being wrong. Otherwise, it would be easy to just ignore very loud people. So I think balancing what is being said compared to how much is being said is it's not easy. Essentially, everything that is posted on this mailing list is biased and is not objective. It's highly subjective, actually. Many of the postings, most of the postings probably, are from submitters, and they have something to personally gain or lose. Definitely the case for me as well. But also companies who are posting, I know that at least for some companies, they've started implementing some of their schemes or started implement systems based on some of the schemes. So they've started investing. And that also means they have something to gain or to lose. If the schemes that they sort of bet on in their early work get standardized, that's going to be good for them, and otherwise they may need to restart from the beginning, at least to some extent. There's also a lot of selection bias, and some of that is natural. So of course you optimize first your own scheme, and some submitting teams, they have a lot of resources, they have big teams behind them, they can optimize code on a variety of platforms and spend a lot of effort on this. When it comes to attacks, it's natural to first pick the low-hanging fruits, but that also means that really complex schemes that are maybe not even that easy to understand, and well, definitely not to find maybe intricate attacks against, they're not so much attacked. They're not so much looked into. There's also selection bias, which is quite interesting in many posts on that mailing list, where you see that, well, you can read through posts where every single statement is technically correct, but the way that certain pieces of information are being put together to tell a story is, well, highly biased. Just by selecting what information you put in and what information you leave out, you can tell a completely different story. And overall, I think this leads to a very incomplete picture of the security and performance of schemes. And maybe this is most drastically the case when we're looking at side channel attack security. So there's now a lot of work going on trying to attack implementations and also propose countermeasures against these attacks. And my impression is that this is really picking the low-hanging fruits. It's looking at the schemes that are, well, first easy to attack, but then also easier to protect afterwards, to come up with countermeasures. And there's, for example, a lot of work on lattice-based chems because they are fairly simple. And there's relatively little work on signatures actually in this domain. Another random thought that I think is, well, at least worth going back to is security level to metric. I'm also realizing that I should get to an end. So in the original call for proposals, NIST said that they want to relate the security to AES and SHA-3. And they said, I have the full quote here, but that they will evaluate that with respect to all metrics that NIST deems to be potentially relevant, and that NIST intends to consider a variety of possible metrics, and will also consider input from the community about this. Understand where this is coming from. It's not easy to come up with a good cost metric for attacks, but I think when running such a competition, fix the attack cost metric when issuing the call for proposals. It is really hard for submitters to choose parameters for a somewhat unknown target if you don't actually know in what metric attacks are being evaluated. And that led to multiple proposals using security claims in subtly different metrics. And in the discussions that NIST was announcing they would be having with the community, they did happen in a way, but they're not cleanly separated from discussions about schemes. Some aspects that should be clarified is what is the aspect of access to memory, cost of access to memory? How does it depend on the size of the memory? How does it depend on if it's quantum memory or if it's quantum access to quantum memory? Some more guidance on how the depth of the quantum circuit influence the cost, I think would also be valuable to have. And there was something on that with the max depth argument in the NIST call, but I think it could be more clarified. And then another thought is it would be, I think, really interesting to think about multi-target security, which was explicitly excluded. That was at least clearly specified. Although NIST also said that they find it interesting, but I think this is actually worth looking into. And then I think maybe a bit of a controversial statement, but ignore classical security. At least when relating to AES and to SHA-3, we at the moment, with the PQ schemes that will be standardized, I think we don't understand the concrete security as well as we do for elliptic curve cryptography. So my advice for anybody deploying anything in the near future would be to use a hybrid combination of post-quantum crypto with elliptic curve crypto. And then the elliptic curve crypto gives you the pre-quantum security, and you don't need to worry about the exact pre-quantum security of the post-quantum scheme. And then in the long term, we don't care anyway if we believe that a quantum computer will be built, because all of this will anyway be broken. So we only care about the quantum security. Some more thoughts. I think it's worth to think about batch signing. Most signatures are computed offline, and we don't care about latency for those signatures. We do care about throughput, though. So if you think about busy certification authorities, they do care about the throughput of signing. And it's very easy to design signatures that have maybe a bad latency, but a much higher throughput by, well, just signing the root of a, well, very little stateful hash-based signature scheme and use all the leaves at the same time. There's probably better ways to do this. And I would be curious to see more elaborate throughput-oriented signature schemes, really optimizing for size of the signature and for throughput and ignoring latency. But that would require a batch API for benchmarking. Another thing to think about are Nikes. There was a posting by John Mattson from, I think, Ericsson, just about a month ago to the NIST PQC forum saying that round 4 of the NIST competition will still be limited to chems and signatures, which is a great start, but clearly limiting. The most obvious thing missing is maybe Nike. I agree with this. I would really like to see post-quantum Nikes being standardized. The reason I think why this isn't happening more at the moment is that there's rather limited set of candidates. The most promising candidate is Seaside by Kastrik, Lange, Martindale, Pani, and Rennes from Asia Crypt 2018. There is another proposal by Azadiraj, Zhao, and Leonardi from SAC 2017, which is considerably less efficient, in particular in terms of sizes that are being transmitted. There's also some work on lattice-based Nike. Lubashevsky described this on Crypto Stack Exchange as a sort of folklore approach. He sketches how this works, and I had to shorten that URL, otherwise this slide would have been overly full. There's a master's thesis by de Kock at TUE, also looking into lattice-based Nike. There is a recent paper showing what the limitations are in terms of performance from PQC 2020. So there's some work in this direction. At the moment, there's not a lot, but I think maybe issuing a call for Nike would be would maybe push a little bit more in this direction. That would be good. Final thought: proofs. I think that too many proofs are simply wrong, and I put here proofs of NIST PQC candidates, but I think that statement is true also for other cryptography. There's just, I think we're not particularly good at getting proofs right. And sometimes the problem is that the theorems are also wrong, and that the proof can't even be fixed without also modifying the theorem. And sometimes that affects security. I mean, obviously it affects security guarantees beginning, but sometimes it actually affects the practical security. There's some examples from the NIST PQC competition, mostly focusing on schemes that I was involved in. There's in Kyber round 1, we compressed the public key, which meant that the reduction from module learning with errors didn't work anymore. Sphinx Plus, you could nitpick and say the proof was correct, but it used an assumption on the hash function that didn't actually hold for the hash function we were using. So you could say the proof was correct, but didn't apply to the scheme it was proving. Then there was this Eurocrypt 2020 paper showing that many schemes had a proof using different random oracles and implemented all of these random oracles through the same non-domain separated hash function, which even led to some attacks. So again, maybe the proof was correct, but it wasn't a proof for the scheme that was being implemented. And more recently, and that is actually also on me, we do one extra hash in Kyber, which makes implementation somewhat easier. But that is something I really, well, we learned fairly recently, creates some issues with the QROM Fujisaki Okamoto proof. How do we get out of this mess? Well, first, I'm not sure how confident we should be in proofs when things are standardized. So several bugs have been found, some have been fixed. Are there more? I don't know, probably. How I believe we get out of this is through high assurance crypto. So through computer verified proofs. That forces the people who write proofs to do it in a really, really tiny step by tiny step way so that computers can understand it. And I think we need to computer verify proofs of security, but also of implementation correctness and of implementation security. And to show how this works, we currently have some work in progress where we're trying to do this for Kyber. We have a high-speed implementation of Kyber in the Jasmine programming language. We have a proof that this implementation matches the spec in EasyCrypt, which is almost done. And we have a proof that this specification matches, actually achieves CCA security, and that proof is also in the EasyCrypt, so also computer verified, and that is also almost done. Matthias Myers gave a talk about this project and some related work in this space at the NIST PQC conference, and here's a link to the slides. With this, I would like to thank you and leave you with some pointers to my website, my email address for questions, and my Twitter handle. Thank you for your attention.